Hi, we are Sensor Dev, and my name is Dana.
My name is Lawrence.
And my name is Lois.
So as part of Sensor Dev, our goal is to design new sensors to detect particles at various stages of the water treatment process. The two sensors that we are working on this semester are the fluidized bed solids detector and the submersible turbidity sensor, which we will talk about later. So the fluidized bed solids detector was created for the high rate sedimentation team because they were trying to design a sedimentation tank that will produce water turbidity at below 0.3 MPU. And for a certain part of their process, they were not able to use a turbidity sensor to measure the turbidity of the water. So we designed a sensor that could wrap around a PVC pipe and then measure the concentration of the particulates in the water. And our focus this semester will be on making the fluidized bed solids detector easier to use and more functional.
So we had a couple of previous models. So the first team to begin working on this was actually the spring 2017 group. And if you can see on the top is the very first model that we had. There were a lot of problems with this, especially because there was some light that came through and that became like a confounding variable. And so then the next iteration during fall 2017 was using foam. And so that was really good because it was flexible, it got rid of all the excess light, and we had a really nice calibration curve. And then this semester we worked on making new modifications to fix all the previous problems that we had.
Yes. So this semester we are implementing a new design, and it's been improved from the previous years to allow a more compact and sturdy casing. And this has a few advantages, including decreasing the amount of light interference, increasing accuracy and precision, creating a more user-friendly interface, and it requires less adjustments, which saves time, but also makes the sensor itself more accurate and less prone to user error. And as you can see in the photos, this is the design that we created using the software Onshape. And eventually this shell came to house both the foam and the photosensor and LED, which you will see in the next few fabrication steps. So for our fabrication steps, we 3D printed the half cylinders with Onshape. Then we added a magnetic clasp to secure the casing so that the user could put our sensor on a PVC pipe just by putting both sides together, and it would hold up by itself. Then we added the electronic components, which includes the LED, the photosensor, and the microcontroller. And then we wired the ProCODA board, and we had to add a 5V to 3V circuit because 5 volts were coming in from ProCODA, but our LED could only take in 3 volts. And as you can see in the photo, the casing houses all of these. So within the casing, we have the foam and both the LED and the photosensor right across from each other, and that will be what's reading the data. And it's going to send back to ProCODA how much light is going through, and eventually, as we will talk about later, we create a calibration curve to make this data into something that's actually meaningful. And here is actually our final product. On both sides, as you can see in the photo, we have the inside of the hard casing shell with the LED and the photosensor, and they're right across from each other. What you can't see is actually the wiring underneath. So connected to both the LED and the photosensor, we have wires that run through that send both signal to ProCODA, which will eventually be used, as we'll talk about later on.
Okay, so as you can see, this is the closed outer casing of the sensor, and it was mainly just made out of a simple 3D printed plastic. And we have the two sides here, and they are connected with a magnetic strip that allows both of them to attach to each other.
So as you can see, this is kind of like a diagram for the ProCODA board. So from ProCODA, like we had cables running into like this ProCODA board, and the ProCODA board had like 4 signal outputs and inputs. So 2 of those were power. Both of them were 5 volts. One for the signal, so for the photosensor, and there was another 5 volts for the LED. One of them was ground and the other one was signal. So what we had to do was we had to connect these different inputs and outputs to our sensors and our LED in order to gain that information and to plug that information into ProCODA. And also, because the ProCODA board outputs 5 volts like we talked about before, we have this problem because the LED only runs on 3 volts. So what we had to do is we had to make a simple circuit to basically voltage divide from 5 volts to 3 volts. And it would use an op amp in order to ensure unity gain. And over here, as you can see on the bottom right, or on the bottom left, I have an image of what a traditional op amp looks like. On the right side, we have the circuit that we actually did use. So, and this is also just a photo of what it ended up looking like. We used the LM324 op amp, as you can see.
So although we finished the fabrication process for the sensor, upon finishing we realized that our circuitry and the way that everything was wired up, the LED wasn't maintaining a constant intensity throughout the lighting process. So we will have to fix that issue, because if we are measuring the concentration of a substance in the water and the light will change its intensity over time, the absorbance measure will vary and that won't produce accurate results. So we will have to finish that, and then after finishing that we will have to calibrate a calibration curve, and we will test it on the PVC pipe, which is the high rate sedimentation apparatus, and then we will also work on the submersible sensor. And as for sensor calibration, we will test the sensor on fluids of different known turbidity, and we will develop a concentration versus absorbance relation with various fluids of different turbidity, and then from that data we can convert the voltage reading from the sensor into absorbance reading, and then we convert that into a concentration reading, and then we can develop a voltage concentration relation that we can use to test on different fluids of different turbidities.
So the previous semester was the first time we started working on the submersible sensor, and the submersible sensor, like we discussed in the symposium, is basically meant for in the flock hopper you want to see how high the sludge blanket is. So what we were working on were 2 different models for a submersible sensor, one of them using an endoscope and another one just using a light sensor and a LED, much like our sensor that we're developing now, except submersible and using a microcontroller instead of through ProCODA. And so we ran into a lot of obstacles in the previous semester. If you can see on the next slide, we show, I listed a couple of the problems. A lot of them were like camera pixel granularity, waterproofing, keeping the endoscope straight, and there was another problem with light gain that we eventually solved. So there were a lot of dead ends to this, but it's still a project that we're going to work on. But because we haven't had the time to work on it this semester, we're probably going to start working on it next semester. So at this time, we will take questions and recommendations through email. Thank you very much.